Hi, Cliff. This is Richard. I'll try to go through this quickly. I have a folder of source code folders that I've been working with. These are samples from GitHub of some of their installation projects, some of their, they call them different things, basically for any particular thing. This is a Python one, and so they have, as you get down there, I'm not sure what the PNG throughput, I don't know all the extensions there, but what I did do, what I normally do is the first thing is I go through and I just search and count how many different extensions there are. So here there are 656,000 files on that in that GitHub folder, the main one, and then they break down this way. So the H, JavaScript, CC, I'm pretty sure is one variety of C++, CPP is definitely Python. JSON is not. I'm not looking at the data types right now. I'm looking at the pure, more or less pure instructions, and then C, Java. Now some of these other ones I don't know. I'm pretty sure this is TypeScript, TS, I think. INP is often one, but I'm just doing a first cut. SH is also a scripting language, and some other ones. So anyway, that's just there. I have a program here. This one is going through, I'm just looking at AstroML, and I'm just looking at CH, Inc, JS, and PY extensions. So I just say, this basically creates a true object for each of those, and then so it's looking for them, and they go in as characters. So if I see that extension, then it gets included, and then I use the same categorization. These are true, and they get excluded. So while on for, the first word is good. Anyway, so I first go out and get the file recs for there. So these are the names. This is the standard file record I generate. It actually gets generated as a TSV, sent back as text, and then I parse it. There are cases where I don't need to parse it, and I just look at them. So I don't know what some of these extensions are. I'll probably have to, eventually I'll have to go through all of them. I have already, believe it or not. I've done this so many times, but each time I start through the same process again. I say, I don't know what's in them. I'll go look, and then eventually I try to do that. So here, so I get the file name. If it's excluded, if these are included extensions, if they're not included extensions, then I skip. Otherwise, I get the name, I read it. If the text has no space equals quote, I'm being very specific. Now Python enforces that, it seems, and it's common in the better languages that they have a space equals space in there, and I haven't done Delphi, which has the colon equal, so I can include anyway. So I come in, I get a line, I trim it. If it has a // in it, then I split it, checked if it's all a // if it's all a comment, and then I take the line part of it, trim that, and then continue. So that I check for the first word is just any alphabetic characters A through Z in the line, looking case insensitive, and then I take that and lowercase it, so I get the first word, and then I exclude while and for, just to trim it down. I've got tons of stuff. Now, what do the results look like? Well, they look like this. They're they're somewhat isolating the thing. So there's the speed of light. I recognize that, and they truncated it. And I have no idea what H is. So DH is probably a speed. 100H is probably a distance. So speed over distance, and this is meters per second divided by meters. It's going to be per second. It'll be a hertz type thing. So then these are just there. So frequency is equal to lambda. I don't know their syntax here. This is kind of odd. I don't know how to interpret, z colon 1 over, I don't know how to even read their language. There's a bunch of functions, okay, like square root, absolute. In every set of things where they get serious about it, that just happens immediately. So I'm going to have to include those in all of what I'm doing. So, well, there are some really odd units. I mean, there's one which is watts per square root of hertz. Okay, and I know what that means. It took me a better part of a year to learn it, and it's not used consistently out there. But you figure these things out. I can remember and code those kinds of things if I have all the pieces readily available. Otherwise, it becomes too burdensome. So anyway, so let me just run another one. So this is here. That's the kind of stuff. Now I don't know what these are. I mean, it looks like a pair, maybe. I don't know. This is the Python. Now transpose, that says in stack, they're basically taking matrices in here, and so and they're doing complex calculation. This one and the last one I looked at both use complex numbers, so they're not doing anything. Okay, this is NP is NumPy, which is a library, and then they're taking pi out of their NumPy arctan2, and I chopped it off. They actually stuck that on the next line, but I'm not trying to run a full parser. I'm just trying to get a rough indication of the types of calculations that these are doing. So these are this NumPy is reasonably. I mean, they did kind of what you're trying to do, was just they got all the units and so there's maybe 10, 20, 50,000 people using that. Could be more, but nobody's winning. There's 1,000 groups of 10,000 out there, and they don't work together. They're all reinventing the same stuff. NumPy is infinite, so they're just not infinite equals not NumPy is infinite of that. So, all right, so let's see. Window size, this is getting into all kinds of things there. This one I picked up, I can't tell their comments. Each one has a comment method, and it's not hard. I just didn't want to implement it here. And so there's that NumPy absolute, again. So some of the syntax in here, they just, there's a lot of string functions, I'd say the majority. Now FFT, there's 30 main FFT packs out there, and this one is not in the NumPy. It's another one that they have in there. Inverse FFT shift, and they're doing a FFT pack. That's a forward one. this H could be for absolute. It can include probably FFT type objects as well. Absolute value of a vector that could be, I don't even try to guess. I know what likely, but I say, okay, go and dig and do the thing. This business of float and all, I don't care about the internal representation. I just want to know, is it meters or feet or power or conductivity or so. All right, let's just keep crunching. So then this is not a bad way to do. This is the way I go through everything. I say, read a few thousand samples and go and look and basically what am I doing? I'm memorizing all the cases that occur, and there's what I'm saying is a high percentage of this is a reference to an array. This is this is also a reference to array, and then there's a bunch of these function calls, and so there's almost nothing that's condensed or collapsed down to things. This notes in here there's a calculation, but the actual numeric calculations are often small compared to the number of things moved around. Let's see what else is going on. Anyway, you got the idea. I'm basically going through and right now I actually did one, let's see, this one. This is my first cut, and I looked at all of these languages first, and then I wanted to dig deeper, so I just took a smaller sample because here I'm reading the files in detail. Okay, let's see. I want to go to. All right, my equations. My list of equations. Let's see. Oh, there. Okay. These are samples. I took a couple of problems that I've been working on. I have 200-300 favorite problems that I work on, and so this one actually came from Wikipedia. It's just a simple RLC circuit, and so I had to go in and translate the abbreviations first. Okay, so E is okay. You can use any word for the display. This is E for the electric field. But what I do is I work with the base unit itself. I say this is a volt per meter. This is a volt. This is a Henry. This is an ampere. This is an ohm. And then which is more fundamental. And then I know how an ohm and an ampere relate. A Henry and an ampere, a volt and a Henry and an ohm, all those. Okay. Omega, radians per second, I don't try to remember the name. I remember the radians per second and do those. So a lot of what I do, because I have to do so many interconversions, it's just what you've done. You say, screw it. I don't care what the name is. I don't care what the value is. What are the units? Let me get that down. So frequency is a generic thing where the units can change, but when you're working with hertz, frequency becomes a broad term, which ties to the hertz central concept. So inductance is a human word, that, and it can change all over the place, but the fundamental piece is the Henry. Now some of these are hard. What I would rather do, what I'm actually doing, this is what comes from the thing, but I normally, I would come in here and I would say, this is volt, and Z is, there's okay, impedance, okay, I would use a volt per something, you can't say ohm, okay, I think that's probably to work with the direct unit, so, and this would be then current, or actually ampere equals volt per ohm. I'm going to just Control Z back a few steps. I want to leave it in its original form, and all, because after going through a couple of examples, like, okay, force equals GMM over R squared. These are concise, but they're not very helpful. I'm not going to force myself to go and use everybody's thing. What I'll do is I'll say newtons equals gravitational constant times kilogram 1, kilogram 2, or mass 1, mass 2, meters squared, like that. Okay, it's much easier to take the sentences, the human sentences of this time, and convert them directly into the final thing. That's an electric field, volts per meter. That's a charge in coulombs. Coulomb is about 6.24 times 10 to the 18th electron charges. Okay. Now here I went through another one. This is one I've worked on in some base units, and I use it a lot. And where I've actually gone to the next stage, and I say frequency. Frequency is a common term that people will use. When you see it, use hertz. Okay. So the base unit, this is defined. This is predefined. And when you say frequency equals hertz, what you're saying is that it has the same units. You don't know the value. You don't care at this point. But it's a substitute or an alias for that. Speed, when you say that word, is an alias for meters per second. Velocity is an alias for meters per second. And I use this exact string in a lot of cases. So when I'm storing things, I'll say, quote, meters per second, and I don't try to say, well, put it in a ASCII only function name or something, or variable name. So anyway, these are there. These I'm getting down. That's why I stopped. Basically, I stopped right here, and I went and built that table of let's see, on the B drive, anytime series. That one. Let's see. All right, so this is the table, and I did extensive cleanup on it. Okay, this was mostly empty. They had mixed text and character. All of these were lowercase and partial, like abbreviations and things. All the magnetic was MAG dot, that kind of stuff. So this is a working column because I'm still revising in there. They got an issue on the name for mass units. So I formalized it. I'm using atomic mass unit. When I get it locked down, I'll make sure that goes in everywhere. These I don't use. I'm trimming them out altogether. Like Coulomb cubed, meter cubed, like that with the bracket, the little thing, because it's not accepted everywhere. I'm collapsing those down to Coulomb 3. Okay, and I'll just use that as my tag for it. So coulombs per meter cubed. This would be, it'll go like that. So I'm not, it's, this one, it's going to be coulombs cubed, meter cubed per joule squared. Okay, so that's that. So I'm getting rid of the negative and the quote. So yeah, there. And this one, oh, that's the second hyperpon. Okay, so this would be coulomb to the fourth, meter to the fourth per joule cubed. And it just simplifies it a little bit. I don't want to, I don't want to muck around like volt. This is volt per meter, okay? And the guys at NIST have too much time on their hands. Some of them are a little bit fussy in the sense of old, made, fussy. Volt per meter squared. Okay, this one ends up being Coulomb squared, which you'll see it a lot because Coulomb squared is a force or a term in the force. Coulomb squared, meter squared per joule. And like so, and you don't need joule to the first if it's they're volt coulombs per meter squared. That's a charge density, surface charge density. That okay. This one got messed up. Meter per second squared per second. So that's what I've been doing. I spent about 5 hours getting this far, and it's still, still pretty messy. But the thing is, when you do this, then the rest of it gets shorter. And believe me, I've been around the drill. Electron volt per Tesla, that's getting to be a common unit. When you collapse these down, they get easier to read. Hertz per Tesla, that's a standard magnetic property. And meter per Tesla. Okay, this one goes in this way. I just invert it. Per meter Tesla, and the implication on these is that they're read continuously. So you put all the products on the top, you put the denominator on the bottom, and that means that you take the meter and the Tesla on the bottom, multiply them through, and then invert it. Kelvin. Okay, so electron volt per Kelvin. I know all these, and I've checked them. Okay, I mean, I spent my life checking every single one of these things many times. So Hertz per Tesla, per Kelvin, sorry. And the thing is I don't want to have to do this again and again. I think I've put in enough 50 years doing this damn stuff, and I don't want to have to go back and say, well, we'll go through the damn list, for the 5,000th time. I say, look, this is the way it needs to go in there, and quit screwing around. These, I've got to go look up. There's a deuteron G factor, which I think is a gyromagnetic factor in there. And it may be a lowercase g the way they normally do it. But most of these are there. Okay, ampere per joule. Okay, so I got pretty close. I mean, a few hours. I could show you what it looked like. Coulomb per kilogram. That's a charge per unit mass. These are pretty routine. When they're down like this, simple ratio things, no extra, thing. Basically, what I'm doing. Okay, so this one, shielded helion magnetic moments. Basically, that's a ratio, and it's here they're looking at the electron magnetic moment divided by the shielded helion magnetic moment. So it's pretty routine. I'll get all of those cleaned up. Coulomb per mole. Okay, this is actually how many coulombs of electron charge are there. Giga electron volt square per giga, like that. Okay. Watt per meter squared, standard intensity for lasers, all kinds of power flows. Okay. Now, putting it in there, meter 2 basically becomes a tag. It's not a, it's not an expression, it's a tag. So watt per meter squared, steradian, okay, meter squared, that's the squared part. And then SR is steradian, and I'll write it out. And in fact, I go so far as, because there's I'll explain this here. I made that capped, all right, because all the prefixes, if I have millisteradian, mega, all the big ones get capped. Okay, I spelled it back. Mega steradian. Pico is small, so it gets lowercase. Peta is big. There. Do you see how that works? And believe me, that just that little thing has simplified my life a lot. That one I'm going to leave. That needs some more. I'm just going to leave it because I don't think it's well done. So here's a Kelvin, and I started it and I got hung in the middle. Kelvin per meter, kilogram per meter, hertz per volt. And I actually, in some cases, I'm saying per, so this is equivalent to hertz per volt. Hertz per volt, like that. Okay. And I'm being rigid and brutal on it because I can't screw around with people anymore. Do it one way, do it the same way every time. Newton per ampere squared. That comes from the current squared in power. Anyway, they're all pretty, and that's a squared, ampere squared. Kilogram meter per second. Okay, and that would be capped. A meter is going to be there, and per second, like that. Let's see. I didn't realize I still had so much. It was a long process to get even to here. So this is per meter per Tesla, and so that would go in this way. And, that whole mess gets dropped out. That whole mess gets dropped out. Much easier to read. Is always, okay, this is electron volts per hertz. And the way I write them, there's no spaces in there, and implicitly I'm going to use that as a not space separated string as an exact identifier. So here's coulomb per kilogram again. Now what'll happen when I count these is there will be a finite number of these, and I'll show you in just a moment. Okay, meter squared, hertz. Okay, this is watts per meter scale. Okay, this is used for a body, like at a given temperature, radiates, and this is the flux of the radiation in watts per meter squared for the given temperature. So you take the temperature, multiply it by take this constant, multiply by the fourth power of the temperature. It tells you what the energy flow is in watts per square meter, the power flow from there. Okay, and that one I've used a lot, and it's worked. Okay, meter squared is just going to be a standard. So, oops. Control Z. Okay, I picked up an error. So meter squared. I have to hit a delete. Okay, I'll check all of these again. So hertz per Kelvin, like that. All right. So now, let's save that. What I want to do is quickly count these. I got the whole table in the existing sheet. I'll just stick it right here, and I want the unit there and I'll count the unit. Okay, so, and then I'll sort this way, and there. So joule meter, atomic mass unit. In this table, I keep count mentally while I'm going through here, and you see that there's a lot of onesie, twosies, and then there's a bunch of these. Now I'll check and see, but all of these are roughly interconvertible, and you see there's some that are missing. So that's my management method there. Now, all these onesies, they really need to be treated that way. They're mostly outliers. People do it, and there are very good reasons for doing it. But the core ones are going to be the energy, joule, meter, atomic mass unit, kilogram mass, joule per Tesla. That's the energy in an electric field. So you got a magnet, and it'll flip back and forth, and that's how much energy it takes to turn the magnet in the magnetic field. Mega electron volt, I would not use that. Basically, I'm going to say that's a non-standard unit. You can enter it in yourself in mega electron volts, but when it gets sent for calculation, it'll be in joules. Okay, so kilogram per mole, the charge, that's got to be expanded quite a bit because we don't keep track of charge per unit mass that well. Proton masses is there's some of these mass ratios, and I double click the number, and so these are some relative masses, and I'll go in and check the definition on those and get it down. I think what that is, it's the electron. This one would be in triton mass ratio, so that can be fixed. This is the tau, as the base mass. So I've already corrected a few of those, so those just need to be done. But the deuteron, electron, alpha, helion, proton, triton, all of those need to be in whatever base unit is. So I have to find out their definition of what the base mass was when they used the word relative atomic mass. So that's just stupid. And I'm going to delete this sheet. There. Okay. So that's really helpful. I use that all the time. So all right. So now I've got now these numbers are correct. I've checked almost all of them, and not just once, but many sources. Okay. So there are some things that there's equations and definitions and measurement methods for all of these. There's probably every person every one of these has like 20 groups around the world who works on it. So these are got an Avogadro's number. I don't even want to count how many of those are. I have this. I'm not even going to bother with it for the most part. Like I say, you get down there, the numbers in there tell you pretty much what it is. So if they throw that many in there, and you look down the column with the things you have to combine it with, you'll quickly see that 5 digits there, and these are mostly, they only come in. This one I use all the time, Avogadro's number, and a few others. There are some that are, in terms of usage, they're used so much more than they have more weight from the usage, not from where they are or what value they have. Boltzmann's constant in here, this number is only good out to about 6 digits, but it is used more than all the rest of them combined. And it doesn't get, in the same way the G gravitational constant and so on. So this table is going to get split. Basically, there's going to be about 60 core units, and the rest are all mostly derived. So, all these, these ratios, those are all going to go in a list of derived things. So I'll add a column in here that says derived, and then I'll sort by that. So I've got probably another 2 days of work on this table before I'm satisfied that it's even at the beginning thing. All right, so there are that many different languages. Yeah. Okay. What else? Let's see. Okay, so these are pretty thing. Some of these, this is not the fantastic simplification occurred when I went and started using potential for this. Okay, a joule per kilogram. There is chemical potential, electrical potential, magnetic potential, gravitational potential, velocity potential. There's a bunch of them. And when they all are in the same units, you can combine them. And that's a drastic simplification of a lot of things. Now, is the underlying process the same? Yes, it's identical if you keep track of the frequency, distribution of matter, basically the 3D scan of the thing down to whatever frequencies spatial frequencies and temporal frequencies you're working with. So that's taken a long time, but it works. It works really well. These kinds of things, okay, there. Now here's the one, I took this from the encyclopedia article on the farad, which is capacitance, and there are all these variations for there. So underlying this, there were some background things. I'm going to put them all in. I will do the substitutions myself, and only the valid ones are going to go in. And if they're like this one, second per ohm, that requires some explanation or like a footnote. I'll flag it and say, don't use this one without checking, right? This only works, this particular thing only works with certain kinds of integrals. When you're monitoring a signal, you have to calculate it in a certain way. If you're doing a measurement, you have to calculate it a certain way. You have to normalize it. There's a, you don't, it's not like 2 plus 2. You go in and you spend 3 weeks on an experiment and you make sure you do it right. So some of these are exact. These here, and that's why when I look at these, I've got to clean that up. Okay. Here, frequency there, that's identical. This is a notation I've had. This is basically A equals, it's an identity, an alias, or a thing. I wrote a program. Okay, this I can read. Okay, so in my program, let me move this off the screen. All right, so that was an earlier part of today where I was working on reading the equations. What I did, that thing here is called list of equations, this page. What I'm doing is I'm reading that, and then I'm going to split it. I put in a tag to say where did the equations begin, okay, there, and I'm basically pre-processing. I'm reading these things down to here. So I just split and get those out in their form. Now let me show you, let's restart that and read equations. Now it'll come in here, so it's going to, I'm keeping count of some things, okay. I'm gonna split the lines. Well, let's just do it. Let's just walk through. So I'll read the equation. So it read the text. It read that. It split them into parts. This is really long, the middle part. And then I'm taking the middle part and trimming it. Okay. And then I'm splitting those on character turn line feet or line feet. I can't remember. And then I got 131 of these where they look like this. Okay. Now I'm going to go through them, and I check if it doesn't have, if If it doesn't have an equal sign in it, then I'm just skipping it. Then I'm splitting it on to see if it has a comment, because a lot of these lines I put comments on them. I don't need that for what I'm doing here. So I'm basically then saying, okay, it's the first part of the line is there. So now I've got my base equation, standard equation I'm working with. And if it's not, if that one doesn't exist, like if you trim it, it skips it. So now what am I going to do with it? Well, I'm going to go in and all right, let's see if I can do it. Okay, so this is the equation. First of all, I'm taking the spaces and I'm removing all the spaces. Okay, so now I got it down to this form, and I'm taking all the words. I split on the what valid operators are allowed in here. Okay. It'll split on squared, star, and slash. Okay, so this is going to get split on the slash in here. And then it'll pull out, basically when it splits that, it gets these words. Okay, so now I've got these unique words. And then I'm creating a holder for the word list. I'm going to, I take the right-hand side of the equation there, and then I'm going to go and process it. So what am I doing? I take the first word, which is from the right, volt per meter. I should have started with the skip the first one. I need to change that. Skip the first one, and basically, what am I doing? You'll see what take the volts per meter, and that was because the first word didn't. Let's just keep. So let's just run it through. Okay, so those are the unique words that were in there. The word list is that one, and the right-hand side now looks like that. Basically, I took the B, the word. There are a bunch of ways to do this, but I wanted to standardize the thing. So the equation, let's see here, the equation is that's the A equals B over C is the generic type of this equation. So it started with this E equals volts per meter, and the right-hand side of this, let's see, where was it? That's the equation. I counted them all. Oh, and then I take the unique words. So I said, for this equation, A equals B divided by C, this is the order of substitution. Take your E, put it in for A, basically what it says, B equals volt, C equals meter, plug it in, and compute E. So it's kind of, I'm trying to process these things, and that's the quickest thing. I mean, it took me 20 minutes to write this, and I don't have a lot of 20 minutes. So all right, so the result of this, so that's what it's sending back. A equals B there. Now I think I'm storing these. I didn't actually keep them. I just ran through them. This was just a preview. So if I do it, so this, take these all out, take that one out. Oh, and here. So the result, so A equals B, L equals Henry. A equals B, L equals Henry. Let's see. I equals ampere. Now you see that this is a tag for what to do with this. It just says, you see this kind of a thing, treat it as A equals B. and I'll just write some routines to do that. I can crank those out, and I can get pretty far down the way because it's not, I'm forcing it to be simple. Okay? We have to change the humans more than we need to change the program. When you go and try to make the program really complicated, then it gets weird. So A equals B there. If I change, I see my error in there. I got to change the drop that first one in the equations. Let's see, that was start with the first word, not the 0th word, but the first word. Okay. Oh, I needed the first one. Let's see. I did only the right-hand side. Okay, so I corrected that. So what I did was I changed this to a 1, and now if I do the equations, then A equals B over C, and the right-hand side, I didn't need to. I was replacing the first word, and I didn't need to. So this works pretty well, at least in terms of simplifying. I'm trying to get down to fewer examples. I'm trying to get down from millions or billions of variations down to a few hundreds of thousands, and then I can have a chance to move forward with this. But ultimately, like if I'm going to clean up the standard, like when on the equations themselves, the equation list itself, basically most of these, about 2/3 of these won't be acceptable. Okay. What you'll have to do is you'll have to go in and say, this won't be allowed. Okay. What I'll do is I'll say volt and ohm and so on. Or if I do put these in, I'll pre-process them and do the substitution so that they're all there. And what will happen is this will be volt over, ampere equals volt over ohm, and that would be a generic equation, right? And you'll know that's a generic equation, and it'll only generic equations that I approve of will go in there. Now, you can do whatever you want. I'm only going to allow things that work to go in there. So, all right, so this one is pretty, you see this a lot, and this is what people memorize, but it's not memorable. You cannot use it in there. I'm going to simplify, even though I wrote it here for JavaScript language. I'll standardize square root. I'll standardize atan2, and just have one there. When you go to implement this particular one, you say, look, I've got an atan2 of AB function. I'll need a routine for that to do the calculation. Then I'll look up the local version and say, I'm in Linux, what do I use? I'm in this world, what do I use? But it'll be the responsibility of the atan2 of A comma B. That's the name of it. Do you get what I'm saying? That's the name of the program. And it's something like, let's see, it'll be called function of, quote, atan2 AB in there, like, no, there, okay, sorry. Stupid thing, okay. You get what I'm saying? That is the exact string name of the thing that does this one. And it's the generic of it, and then I'll have the specifics there. So we'll send in a packet for the first value, and I'll look at the units in there and deal with them. I'm probably saying too many things. Either you already did it, or you were going a different direction. I don't know. But this I can manage. Okay, I can go in there and I can say I've got a square root of a there, and again I'm going to say the square root. Oh, for in here, you can't. This is not an acceptable form, at least not at this level. I'll basically say you can't. We're not going to use that one. If you want to do the Q using this, you need to name L over C first and put it in. And I think it's the square of the frequency. So you'll put a squared frequency in there. Okay. Or actually, it's yeah, I think that's what it is. I'll have to go look. The reason I don't use these L over C is because I can't do the unit conversions in my head instantaneously. I have to look up L in my head. I have to look up C, get the units of each, compare those units, and write them out in my head, and I'll compare them to R and Q. I have to do all those lookups, and it takes like 10 or 20 steps for me to mentally go through all the conversions. The computer could do that. So this is a square, any function. This is an ohm over here with an impedance, a resistance. Any squared ohm factor can go in there. So this one, if you say that's R times R, ohm times ohm, this is ohm times ohm. So, and when you add those, it stays ohms. Anytime there, you can just take it and say, give me the square root of it, and I got an ohm thing. So there's a bunch that, in a sense, that can be made trivial. And you say, look, what can I get? I can take any squared ohm and square root it and get me an ohm out of it. And some case, and there's a story that goes with every one of them. So for this particular equation, I can write the story of it. I'll leave that in there for now. I'll deal with it. So there, this one is only partially true. In a lot of like transistor, they're like I was looking at transistors and diodes yesterday. Okay, so I'm going through all of those equations, and what I'm finding is that only in certain regions are these things true. That's a linear region where the curve, the response characteristics of the device are linear, and it's and that can be, you have a curve. Oh, I can't draw a curve. You have a curve. It's coming in and swooping along. There might be like a tiny section where that's actually true. What I put in is the actual equation, so that you basically calculate it. You take what this is the derivative of the current with respect to voltage. So we use the differential form and do it on a curve and interpolate and get the Z value for that particular current and voltage value. So it's actually ends up being a lookup. Say, what is the Z when I have this current and this voltage? And either do it by a table. There's a lot of stuff I can do by table, and some of them I can do it by like a thing. If you know the current, what is the voltage, and you can, for this device, you can do it. Okay, let me do one last thing. Let's see. All right, these guys, they can be treated the same way. B is in Tesla, S is a surface, S is Tesla meter squared, d by dt is 1 over time. So this is Tesla meter squared per second. Okay. And this over here, that's a surface. This is meter squared. This is Tesla per second times meter squared. This is meter squared, meter cubed, meter squared, meter squared, meter cubed. That's a density. Kilograms per meter cubed times volume, meter cubed, is kilograms. And this is that's the charge density. So this is coulombs per meter squared. This is coulombs. Coulombs per meter squared times meter, coulombs per meter cubed times meter cubed is coulombs. Joules, amperes per meter squared times meter squared equals amperes. Magnetic. Okay, let's just look at these. These all are readable. They're not that difficult. Volts per meter times meters squared is volt meters. Oh God, these have units, and it's hard in here. This is going to be coulombs over that thingy, which has units of farads. So coulomb per farad is a volt, should be a voltmeter, volt times a meter. So this is volt per meter times meter squared. Tesla meter squared. Tesla, the grad function is 1 over meters. Okay, so if you see a del or a grad curl, 1 over meters, meter per meter. So this is cool. Okay, this is volts per meter times 1 over meter is volts per meter squared, which is Tesla per second, which is Webers per meter squared per second. Okay, so all of these units, the curl of B is in Tesla per meter when you do that one. Mu naught is in henries per meter. J is in amperes per meter squared. Farads per meter, volts per meter per second. So all of these equations, they're all that sum. This is just a replication of the other one. Volts per meters times meter squared per meter times volts per meter is volts per meter squared times a volume is voltmeter. Okay, so they're basically integrating. What are they doing? They're taking the value of E, the electric field at any point, and they're just adding it up. They're going along a pathway on a surface, and they're adding up the value for it. Now you want to add up equal parts, so you break the area up into pieces, and you break the volume up into pieces, and then you just add up as you go across. So anyway, there's nothing here. Per meter, volts per meter, per meter, Tesla per second. A Tesla is a Weber per meter squared. So a Weber per second is a volt. I've done these hundreds of thousands of times, so it's not that difficult. This is particularly useful. This needs to go into all kinds of places. That's the phase velocity, and this is pretty fundamental. What they are not showing in here is that the speed, basically that this stuff in here, mu naught, epsilon naught, if you square this, you get the phase velocity squared, and this becomes 1 over c squared times the relative permeability, the relative permittivity of the vacuum separated out, and then this becomes c squared, v squared, phase velocity equals 1 over that. And so anyway, there's some good substitute. All of this is that we already did those. The current amperes per meter, ampere per meter, coulomb per meter squared, coulomb per meter squared per second, that kind of thing, times meter squared, coulombs per second, amperes, amperes, amperes per square meter, amperes, amperes. These are funky. Those are ampere meters. The units all work. Basically, what this is the magnetization inside a like a permanent magnet, often, or a solid material, or a gas on a short time scale. And what this is saying is that the magnetic field that goes in there has local effects. And so if you try to do something, you get the field that you want to do things with, but then you have to subtract off the response of the material itself. It pulls down or dampens or loses or goes on, less than you want it to be, because it's absorbing some of the energy. This is in field units, Teslas, Tesla, this would be Tesla, ampere per meter, that kind of thing, or ampere meter. I forget which way they did this one. And then, but you can, the fundamental part is the magnetic energy, the magnetization energy, the applied energy, all have to be consistent. And so you're saying, if you flip it over there, anyway, all right. So polarization, all of these processes, they're every person who studies electrodynamics has to go memorize all this stuff, but it's not that difficult. These look hard, but when you take them in units, volts per meter, volt seconds per meter per second, volts per this partial is that's a volt. Okay, this is a per meter, so that's a volt per meter. This is a volt per meter. This symbol has a per meter dimension to it. That symbol has a per meter dimension to it. That symbol has a per meter thing, per meter. Okay, and so this is magnetic. It says potential, but it's not quite. This is Tesla. That's a per meter. This has to be a Tesla meter per meter. You get what I'm saying? So you just did this is Tesla on this side. That has per meter. So this has to be Tesla meters. So the unit of A is Tesla meters. Okay, Tesla meters, volts per meter, volts per meter. This has to be volt per meter, volt seconds per meter. Okay, all right. Sorry, I'm tired. But all of these, okay, so they're not that hard. Okay, all blah 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 blah. These notations get sucky as everything, but a lot of them, you just do it. You got to find one example sometimes where you can break it out, just see exactly what does that function. What are they implying that they want you to do in there? So it's like a really, 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 really shorthand way of saying, go do all these things. And if you've got graduate students who'll spend 5 years working on it, you just say, go do those things. And then they slave and do, sorry, I have some hateful memories back there. Not me, I wouldn't do that, but all the poor bastards who had to go through that. So fields, these are just, I'll skip those, blah, 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 blah. All right, so let's see. Everybody's doing different things. These I use a lot, and basically they're greatly simplified Schrodinger solutions. Okay, you take the Schrodinger nonlinear wave equation in 3 dimensions. You solve it for a bound system, and then it has, in its simplest form, it has magnetic dipole moments, magnetic dipole moments, magnetic dipole moments, which are equivalent to field units. So if this is a fluid, then the fluid flow velocity, the velocity potential of some hypothetical fluid, and the magnetic field properties, you can basically say, well, this is the same as this is the same as this is the same. Okay, so you can do it, and it basically ends up being the same thing. So if you have a velocity potential, it's a velocity squared. That's the same as a joules per kilogram, and it's the same whatever units you're in. So regardless of what representation, if you say, well, calculate with it, show me the numbers, then those numbers have to be in joules per kilogram, and they have to match the experiment or be out there for people to test. If it's wrong, you find it, fix it, move on. If it's right, you use it, and hopefully can trust it enough to push the start button on your starship and not be afraid that it'll blow up. So anyway, let's see. They did this. C squared is a velocity potential. Okay, it happens to be the average velocity of the particles, gravitons in our region of space. That's the way I think about it, and it works. G is the big G, which is just for GMM over R squared. This thing here you'd have to go through. This one, you can say B, the units of B have to be time per unit, time per meter times the units of E, right? So, and this one here, that's a density, a mass density, which you can multiply in here. So this has unit, which fix E. You can use this to fix B. Take that one. You can put this in and work back what G has to be, whichever. Anyway, so that's doable. Meters per second, Tesla, volt per meter, Coulomb, newtons, kilogram, newtons, volts per meter, meter per second, Tesla. And it turns out, let's see, did they do it? This wasn't a great simplification. I don't know who these guys are. They didn't have to go that way. Lens theory per se. All right, let me stop here. You can take any of these things. Okay, that looks really complicated. And it's oh my God, that's terrible. No, distance squared, meters squared. This is meters per second squared times second squared, meters squared, meters squared. This is probably also meters squared, but you can check that this is a 1, so that has to be meters squared. This god-awful mess thing here, you just work backwards. So meters second, meters per second, meters squared. Let's see, meters per second, seconds. It becomes meters squared, probably meters cubed. You see, you just work C cubed. So I would take the C squared out of here. Look how many god-awful places they leave it in there. There's much more compact, fast ways to do this thing. This is doing it the hard way. It's how everybody starts, but it just is hard to do any calculations with it. So anyway, I can take these apart. They take me a while, and almost all of them, you need the picture, the diagram. Everything has to be labeled. You need the units. You better check the damn units. They often don't tell you. You need to look up how did they actually implement this. Did anybody really calculate with this? If they didn't, you might probably just say, screw that, I'm not going to bother with them. This is a ratio of two potentials. That's joules per kilogram. That means this is probably joules per kilogram, and this, I think, is dimensionless, which is unfortunate. So it's basically saying I have a potential out there which is related to c squared, which I call the universal potential. Here you have another one, universal. Anyway, so all of it. What's missing on Wikipedia, and I'm going to take a copy and do it myself. I'm going to try to change them. They're not going to listen. I'm not going to try to change them. I'll put in an equation number. This will be Lenz-Thurring precession 22 or something like that. And it'll be stuck. Okay, so you can't change it back very easily. So once so if this is curl of this this potential field, so the magnetic thing. This one, this is a fantastic simplification of a dipole magnetic field, and this is better done in electromagnetic units. They're screwing around and using a simplification of a simplification of a simplification, throwing out terms, and then leaving you with this god-awful, shorthand that help them think about something, but you can't do anything with it. It's not complete. They left out too much. There's no units. You can't get anything built with it. So anyway, mass times energy. No, mass times electric field. No, that doesn't even work. So they're changing the units of these things, and you just have to go and check. They use the same symbols. They didn't specify what they are. So this is V cross B probably, and the M. No, it should be M is charge. Okay, if that's newtons, that's velocity. Tesla, then this has to be charge, coulombs. Coulombs, volts per meter. Volt meter per coulomb is a joule per meter, which is a newton. So that their M is, no, that's wrong. That's just stupid. I'm sorry. There's a case that's wrong. A mass means kilograms, and what this is coulombs. Okay, you can't, All right, let me stop here.